All right, good afternoon. Welcome back. Oh, that's not on. That would be a thing. There we go. All right, so lab 4 grades are back. So there's no feedback on it, so I'll upload to your repository the actual breakdown of the marks. I've already posted what TAs graded what part. So lab 4 stuff I'll upload when I get back on the train after this lecture. So lab 5 going-ish, going okay. I added more test cases to lab 5. You guys are oddly quiet. I don't know if it means you haven't started yet, which isn't good. Yeah.
Could you add a little more description about like the functions you wrote and like you know what I mean? Because like the instructions on the document, I don't know if it was like on purpose. It was like pretty short.
Yeah.
Vague.
Yeah, because you're meant to read it a little bit. Because the lab, you're only writing like 100 lines of code, if that.
Okay.
So yeah, mostly it's reading. I can add a bit, just ask questions if you have more. I think I answered the same thing. It's like, you don't need that many functions to actually do this lab. So you can ask, but yeah, you can ask, I'll add more context to it. But yeah, part of it was reading it, but I can add more context if you want.
Yeah, I'm a very spoiled software guy. And I like doc strings and like very clearly labeled like, oh, this does this.
Okay. All right, well, I'll do that after, so. Yeah, all right, so today, page replacement. So the fun stuff. So we've kind of explored disk, we've explored memory, we've explored CPUs, and know that each of them kind of have its own cache. What we've been talking about so far, fastest speed memory on your computer are the registers, which are on the CPU. They're going to be the fastest things, but there's always this capacity, speed trade-off, and also the speed trade-off is typically also a price trade-off. So you have a few registers, they're really, really fast, but there's not very many of them. Maybe there's only 64, 32 even, maybe even 16 on some systems. Then below that, there is RAM actually on your CPU die itself that caches, it acts as a cache for the memory. And typically this will be a bit bigger. It'll be like in the megabyte size. Some of the big ones now have like 128 megabyte L3 cache or whatever. So that's as quick as you can get on your CPU, but capacity is bigger, but it's going to be slower, and there's different levels of cache. Each are smaller and less capacity than the other ones. So below that is memory. So that's RAM, your random access memory, all of your volatile memory that gets wiped whenever you reboot your computer. That's pretty fast, the capacity is pretty good, and it's not that expensive, and that's typically in the gigabyte ranges. So like 64 gigabytes of memory is not typically uncommon now. And then below that, there's your NVMe, so that's starting to get into the disk drives. That's what we talked about a few lectures ago. So the fastest version of that is called NVMe. So that's non-volatile memory. So it uses some principles of memory, but whenever you power down your machine and power it back up, all your files are still there. So that's the non-volatile part of it. Then below that are SSDs, or solid state disks, which are going to be higher capacity and cheaper, but also a lot slower. And then below that, there's hard disk drives, which many of you have never seen before. Those are the mechanical drives that go around. Sometimes people call them spinning rust because they like making fun of them. And then below this, you'll see tape drives. I guarantee none of you have ever seen tape drives. Wait, how many of you have ever saw like a VHS tape? We got a few VHSers. Oh, we got excited VHS. Is that like nostalgic now? Okay, cool. So the tape technology, like it writes stuff directly on a tape. Well, that actually applies to computers too. And they can actually store, if you go super crazy with it, tapes can store terabytes and terabytes of information, and they are dirt cheap, but they are also dirt slow. But that is something like Google and IBM and all those companies that store massive amounts of archival data that will never be written again, or that they will use very, very infrequently are actually written to tape drives, kind of like a VHS tape, but they are like, they will actually store like terabytes of information, but they're really, really slow because if you can look at YouTube and see some of these videos, so there's actual physical tapes, and if you want to retrieve information, you get to see the machine go physically grab a tape, put it in the machine, and then read it really, really slow. So that's actually used, but no one in their sane mind is going to use it. Yep.
Do floppies also use tape?
Yeah, so floppy drives are like magnetic, but their capacity is really, really bad. The floppy drives are like 1.4 megabytes, so no one's ever going to really use those. And the like actual floppy disks that actually flop, I forget how big those are, but those are even before my time. But yeah, they're just old. But it's the same principle. It's like magnetic disk storage, kind of. Okay, so part of this diagram for all the memory, if you are properly using the memory hierarchies, you want to create this fun little illusion where each level pretends to be as fast as the speed above it, but have the capacity of the layer below it. So if you're using the disk, like non-volatile memory, like a really fast SSD drive, ideally you want it to be as fast as memory, but also have its own capacity. And maybe even a higher capacity if there's even a slower disk on the drive or slower disk on the machine that is bigger. So we can use this. Today we'll be talking about kind of bridging this gap between persistent storage and your actual physical RAM or actual memory on the machine. So when you're using your machine, you're using your processes, you might notice that even if you look at the actual RAM used by a process, the total amount of RAM used by every single process on your machine can actually exceed the amount of physical RAM on your machine, even though it's all in use. So how it does this is it will go ahead and cache any memory that's not in use and throw it on the disk drive. So if you need it, it can go grab it from the disk drive. If you don't, it just stays there and it can swap in and out whenever it wants. So you might notice this whenever your computer is running slow, or has anyone ever seen a file on Windows called the page file or the swap file or something like that? So if some of you go browsing around, where is it, C Windows or something like that, or maybe it's in the root drive, I forget, there's a gigantic file that's like 8 gigabytes or something like that says PageSys or something like that. That's basically a cache for your RAM that if you actually run out of physical memory, it will start offloading some of that storage to that file, which would be on disk. So the idea behind that is you only keep pages in memory that are actually referenced, and then you put others on disk. And sometimes you have the nice property like we saw before, if your disk block sizes are the same as your page sizes, well, you can just throw them on there kind of willy-nilly. And whenever you need to access that information again, you can read it back from disk and put it back into memory whenever you need it. So today we will be talking about page replacement algorithms, which is just picking which memory to swap to disk when you need to access something that is not currently in memory. So there's 4 main algorithms we'll go over today. There's optimal, which is just replace the page that won't be used for the longest. And this is completely impractical because this is looking into the future, and it's mostly just for evaluating your page algorithm, knowing what the benchmark is for the best you can do. And then there's another strategy which might be intriguing and easy to implement. There's random page replacement, where you just randomly throw a page to disk and swap it out. Then there's also our good old first in, first out, which would replace the oldest page first. We've been using first in, first out. That seems to be like the default for every single problem we have to do in operating systems. And then the last one we'll look into today is least recently used. So the idea behind that is we replace the page that hasn't been used in the longest time, because the process is probably done with that for now, and it's accessing other pages. So for all of this, we're going to assume that it's like a silly assumption, but we'll assume that our physical memory can only hold 4 pages at a time. And whenever we access memory, we want it to be, or whenever we access a page, we want it to be in memory. But initially, all of the pages are already on disk, just so we have something to do. And we'll use this for every lecture, or every example in this lecture. So our goal for page replacement is whenever you swap in a page, you want to swap in a page that will be used continually, and our goal is to reduce the number of page faults, because each page fault is terribly slow because it actually has to read it physically from disk, which, as we know, is a lot slower than actual memory. So that's our criteria, is basically the number of page faults. Yep. Yeah, so in this case, so we can generate page faults a few ways. So page faults can just be that it's not mapped, or you can use page faults for other things. So like Lab 5, you're using page faults for copy on write. For this, we're going to use page faults to actually read in information from disk. So you can use page faults for a variety of different purposes, and this is just another one of kind of fooling the system to thinking it has more memory accessible than it actually has. So again, we're assuming our physical memory only holds 4 pages, and then I'll just tell you the accesses in terms of what page it accesses. So in this example, we're accessing page 1, 2, 3, 4, then 1, 2, 5, 1, 2, 3, 4, 5. So at the top of all these, I'll put whatever page we're accessing. So in this case, we're accessing page 1, and within the box at the bottom is what is currently in physical memory. And whenever I color a page red in physical memory, that means we read it from disk and we put it into physical memory. So if our first access into page 1, initially there'd be nothing in memory because that is our assumption. So I would have to read it from disk and read that page into memory. So it is now red, indicating a page fault, and I read it from the disk into memory. All right, same page, have to say that joke. All right, so now if I access page 2, also not in memory, so I have to bring it to disk. Or sorry, I have to read it from disk into memory. So I would read page 2, and I can hold 4 pages in memory, so I don't have to kick anything out. So I would just have page 1 and 2 in memory now. Similarly, for page 3, same thing. I read it from disk, put it into memory, and now it is in memory. I can hold 4 pages, so I'm still good. Now I access page 4. Same idea. It's not in memory yet. I read it from disk. Now it's in memory, and now my memory is full because it's at capacity because I can only hold 4 pages. So now if I try and access page 1, I don't have to read anything from disk because I already have it in memory. So now there's nothing read, there's no pages in red because it's already in memory. I don't have to do anything. You could also think of this as a cache hit if you want, or whatever you want. So same thing is going to happen for page 2. It's already in memory, no problem there, don't have to do anything. So the interesting thing happens when we access page 5. So when we access page 5, we need to bring it into memory. But in this case, since it's full, we have to kick something out. So now our problem is we have to kick out either 1, 2, 3, or 4. And which one would we like to kick out? So votes for kicking out 1. Oh, we like 1. Votes for kicking out 2. Votes for kicking out 3. Some of us don't like 3. Votes for kicking out 4. Most of us don't like 4. So more enthusiastic for 4. So this one says we're trying to do the optimal thing. So let's do a hypothetical and do what no one wanted. So if we kick out page 1 now, so we replace page 1 with page 5 in memory, then whenever we do the next access of page 1, well, we just kicked it out, so we have to reload it again, so that's a big waste of time. So if we're doing the optimal thing, we will kick out whatever page is not, or whatever page is not going to be used for the longest time. So you can start at 5 and then go up to argue about it until you have 1 page remaining. So between page 1, 2, 3, and 4, well, the next page I access is 1, so I'm not going to kick it out. Then after that, I access page 2, so I'm not going to kick it out. Then after that, I access page 3, so I'm not going to kick it out. And then at this point, I only have 1 page remaining, so I would kick out page 4. So I now replace page 4 with page 5. Yep.
But then, like, eventually we still have to remove one of them, right? So,
Yeah, so I removed 4.
but then, like, whether we remove 1 or 4, we're doing only 1 removal. Is that not like a criteria?
So I still have to swap it out because it's not in memory, but I just have to pick something to kick out. Right? So if I picked 1 to kick out, you know, in the next access, it wouldn't be in and I'd have to load it back again. Right?
You have to load back 4 eventually, I guess.
Yeah, you have to load back 4 eventually in this case. But it also might be the case that I never access 4 again. Or something else, and it could be way longer than this, but this is like it's hard to get like big picture examples from this because I have to fit it on a slide and explain it. So now because we replaced page 4 with page 5, well, we essentially looked at the future, so our next 3 accesses are all going to already be in memory, so we're all good. We access page 1, already there, don't have to load it from disk. Page 2, same idea. Page 3, same idea. And now we get to page 4. So now when we are loading in page 4, well, we're stuck. We actually have to load it in to memory now, and we need to kick out a page. So we can kick out 1, 2, 3, or 5. And in this case, there's a bunch of correct answers. It's just, if I look ahead, my next access is to 5, so I don't want to replace page 5 because I would just have to reload it again anyways, which would be slow. But I don't use 1, 2, or 3 anytime in the future, so I can pick any one of those in this case to kick out. In this case, I'll just kick out 1, so I would replace page 1 with page 4, and then I'm good. Next access is page 5. It's already in the cache. Yep, or memory.
Is it maybe optimal in the sense that you're offsetting the time until the next page replacement by the maximum amount? Because it seems like the total number of page replacements is the same.
Yeah, so we'll see in other examples with the same sequence. So it's optimal in the sense that we're reducing the number of page faults because we're delaying it as long as possible. So for this case, we didn't have to reload anything for like 3 accesses in a row. While if we picked the wrong thing, we would have had to reload it immediately, right? Yeah.
But there are sequences where you would end up with the same total number of page faults, but just they come sooner, right? And that's what you're trying to avoid.
Yeah, here we're trying to just minimize the number of page faults. And if we look into the future, that's the lowest number of page faults we can get for that sequence. There's another question, no? Yeah.
I'm still a little confused. How does it know like which one is used? Like, replace the page that won't be used for the longest. How does it know which one that is?
Yeah, so the question is, how do we know which one? So in this case, we have the sequence and we can look at it. So this is just to evaluate them because we're looking in the future. So
We already know the entire sequence.
yeah, so in this case, we already know the entire sequence. So this is mostly, if we are analyzing these types of algorithms, well, you would record the number of page accesses and then analyze it after the fact, and you can compare it to the optimal. So here, our goal of this is just to count the number of page faults. In this case, makes it really easy. You just count the number of red numbers. So for this sequence, with this algorithm, there are 6 page faults. So we can remember that because we'll very shortly make very poor decisions. So poor decision, let's use FIFO because we always use FIFO as like a first try thing. So same accesses, same problem, except this time we're not doing optimal. We're doing first in, first out, which will not look at the future. so you'll probably find it make a bunch of very poor and borderline silly decisions. So the only thing we can't avoid is the 4 accesses at the beginning because there's nothing in memory. So the first 4 are going to look the same, where we have to bring them into memory from disk. So everyone okay with doing that, so I can just skip it for the rest of the other ones? Okay, so the next access, going to follow the same suit as optimal. We're accessing page 1, already in memory, no problem, already there. Our next access, page 2, already in memory, no problem, already there. Now, here's our decision. So now we can't look into the future. We have to look into the past. So we'd want to access page 5. It is not in memory. We have to kick something out. So we have to kick out 1, 2, 3, or 4. So between 1, 2, 3, or 4, what did we add first? So 1, anyone? So 1 was the first access, so that was the first thing we added in memory, and you can pretty much look backwards and see that, oh yeah, we added 1 to memory first, so that's the first one we got to kick out. So if we're doing FIFO, I added 1 first, so it's the first one out. So we replace 1 with page 5, which you can see is going to be a bit of a problem. So we just kicked out page 1, replaced it with page 5, and now our next access is page 1. Crap, I just kicked it out. So I have to reload it again from the disk. So now I have to pick, do I kick out page 5, page 2, page 3, or page 4? Well, yeah, in this case, I would have to pick out page 2 because that is with all the ones remaining, that's the oldest one. And it also kind of looks like a diagonal line when you look at it with the red numbers like this, so that's an easy way to do it really, really fast. So I had to kick out number 2. So now in memory, I have 5, 1, 3, and 4, and then I do my next access. My next access is to page 2. The one I just kicked out. Oh, geez, this sucks. So I have to pick one to replace. Now I replace page 3 because it's the oldest one. All right, great. Doing a great job here. Now I access page 3, the one I just kicked out again. So I have to do this again. And the oldest one now is page 4, so I kick it out. Oh, okay, my next access is to page 4. Wow, I'm doing a real good job here. And you can see how this is kind of a crappy approach. So between what is remaining in memory now, 5, 1, 2, and 3, 5 is now the oldest, so I kick it out. So I replace 5 with 4, and now I have 4, 1, 2, 3 in memory. And now I finally access page 5, which again, I have to bring back in, and now my oldest is 1. So this would be my final access where I bring it in. So now if I count the number of page faults here or count the number of red, which there is an access, which there is a lot of, how many page faults do I have now? I'll pretend I heard 10. Yeah, I see 10 mouth. So now I have 10 page faults. So this decision was clearly the bad one. So optimal was 6. And now if I did FIFO, I did 10. So it was way, way worse for this memory trace. So any questions about that? Yep.
Why don't we replace individual bytes instead of pages?
So the question is, why don't we replace individual bytes instead of pages? So if we replace individual bytes instead of pages, first, your hard disk does not like accessing bytes. It only accesses blocks at a time. And 2, it's the same reason why we do it for our memory subsystem, because things are really, really slow. So if we can bring in a page at a time, it's way faster. Yep, good question though. Okay, so let's do something fun. So this was FIFO. We had 4 pages we could hold in memory. So let's do this again. Same sequence, same everything, except now I have less memory. So I only have 3 pages I can hold in memory. So if I can only hold 3 pages in memory, my memory is smaller. That kind of makes me suspect that I should have more page faults because I have less room to store things, sorry. So if I have less memory, it makes sense that I have more page faults, right? Because I have less room to store stuff. Everyone agree with that? Or the other way, if I have more memory, I should have less page faults. Yep. Kind of, yeah. Okay, yeah, so what you might expect by looking at this is, okay, well, let's go the other way. So if I have more pages, I will have less page faults. So if I started here where I had 4, well, if I can hold 5 pages in memory, I'll just have the 5 page faults when I initially load them in, and then that's it because I can fit everything. So if I have 5 pages, I'll have 5 page faults. If I have 4 pages in memory, I have 10 page faults. You might expect that trend to continue where if I have 3 pages or less physical memory, I'll have more page faults because it won't fit. But let's just make it smaller now. So we'll do the same FIFO thing, but instead of this time, instead of having 4 pages, we can only hold 3 pages in memory. So our first 3 accesses are going to be the same because we need to load it into memory from disk. So now this will kind of give us the intuition behind it that this is bad because whenever we access page 4, well, that generates a page fault and we have to kick something out, which should be worse than before because we didn't even have to kick something out whenever we access page 4 because we had room for it. So if we access page 4, we have to kick out 1, 2, or 3. In this case, it's FIFO again, so we're going to kick out page 1. So we kick out page 1, load in 4, and this is what our access looks like. And now it's looking real bad for this because our next access is to page 1, which we just kicked out. So we're going to have to load it back into memory, and we're going to have to kick out the oldest one, which would be page 2, which looks real bad. So now we have 5 page faults in a row. We're not doing too good. So our next access is to page 2, which again, we just kicked out of memory. We are doing very, very crappy here. So we have to kick out whatever the oldest one is. In this case, it's page 3. So we would replace page 3 with page 2. Okay, so things still aren't looking good. So our next access is to page 5. We have to bring it into memory. We have to kick out the oldest one, which if we're doing that waterfall thing is now page 4. So we kick out page 4, replace it with 5. So everyone on the same track right now? We're all good? Okay, so this is where our luck changes a little bit. So now our next access is to page 1. Thankfully, it's already in memory. So that is a hit and not a page fault. So that's good. Next access is to page 2. Already in memory. We're all good. Next one is to page 3. Page 3, we have to load in from disk into memory and replace the oldest one. In this case, the oldest one is page 1 again. So we replace page 1 with page 3. So now in memory, we have 5, 3, and 2. Now we're going to access page 4. When we access page 4, we replace 2 because that is now the oldest one. So now in memory, we'll have 5, 3, and 4. And then our last access is to page 5, which thankfully is already there. So now we have this. So how many page faults is that? 9, which is less than before. So we have less memory and less page faults, which seems a bit weird. So if you took that to its extreme, if you want to speed up your computer and make page faults less common, just get a smaller hard drive, right? It's everyone's solution to everything. So that might imply that this isn't used. So this thing actually has,
Are we sure it's not just a coincidence?
Yeah.
Like,
So
is it always the case, or maybe it's just like for that sequence, having a smaller page size means less page faults?
Yeah, so the question is that always the case? And the answer is someone has gone far into depth for that problem. So there's a name for this. So it's called Belladay's anomaly, and it actually formalizes it more. And it says, in general, more page frames cause more page faults. And this is a problem with all of the FIFO algorithms. It doesn't exist in an least recently used, or LRU, that we'll see much later, or stack-based ones. So in fact, for that question, they actually wrote a paper about it. Some mathematical people wrote a paper that's in Greek that I can't read, but they figured it out in like 2010 that it's actually unbounded. So given any sequence or any combination of it, you can come up with a sequence that gets an arbitrary number of page faults. So that's fun. If you really like math, you can go read that paper. If you have any questions about that paper, don't ask me because, yeah, I did engineering, not math. So for all other algorithms, your intuition is correct, where if you increase the number of page frames or increase the amount of memory you have, it will decrease the number of page faults, which is more what you actually expect. So this is just for FIFO algorithms, which is kind of a fun thing. All right, so last one for the day. We'll do least recently used. Is that a question? Yeah. Yeah, so if you go with the extreme cases, you can come up with different ones, but this is like, yeah, for the non-trivial cases, they can come up with any one. Okay, but for us, we don't really care because we're not going to use FIFO because it's garbage. So the first one we actually will use, which we'll see is kind of impractical, but we can actually argue about it, is least recently used. So it doesn't look into the future, it just looks at the usage pattern in the past to kind of predict the future. So again, same accesses, same everything as before. We'll go back to 4 pages and do the same and do the same accesses. So our first 4 going to look exactly the same, where we have to bring it into memory from disk. Then again, our next 2 accesses are going to be the same. So 1 and 2 are already in memory, so we don't have to replace anything. So we're all good. So our first question comes in now is, now if we are replacing, or if we need to read in page 5, again, we need to replace page 1, 2, 3, or 4. So least recently used is, as the name implies, you go backwards in time, and whatever has been used, or whatever is the least recently used, or whatever hasn't been used in the longest, is the one you kick out. So if we start at page 5 and look backwards, well, right before 5, we use page 2, so we're not going to kick out page 2, so it's safe. Then we look at then it accesses page 1 if we go backwards, so we're not going to kick out page 1, so it's safe. And then if we look back another one, it used 4, so we're not going to kick out 4, so it's safe. So there's only 1 page remaining in memory, and that's poor old 3. So 3 hasn't been used in the longest, so it's out of here. So we would replace 5 with 3. So any question about that? Fairly-ish straightforward. Okay, so now we actually made a good decision this time for a change. So our next access is to page 1, and this is typically how memory accesses actually happen on your machine. If you use a page, typically you're running a program, something like that, you'll access the next thing in the array, which will typically be on the same page, or you'll execute the next instruction, which will probably also be on the same page. So this is more like memory access patterns you'll actually see on your machine. So access page 1, we're all good, it's already there, so we don't have to replace anything. Then we access page 2, again, already there, don't have to kick anything out. Now when we access page 3, oh, shucks, now we have to kick something out again. So again, we look backwards in times to see what has been used least recently. So if we go backwards, we can't kick out 2 because it was used right before. 2 safe. We also can't kick out 1 because it was just used, so 1 safe. And we also can't kick out 5 because it was used right before that, so 5 safe. So by process of elimination, 4 is the one we kick out, which will prove to be a bad decision, but hey, we made it. So we kick out 4 and we replace it with 3, and now we access page 4, which unfortunately we just kicked out. So it will do the same thing. So we'll look backwards. We have to kick out page 1, 2, 3, or 5. So we'll go backwards. So we're not kicking out page 3. We're not kicking out page 2. We're not kicking out page 1. We're kicking out page 5, which again, unlucky decision. So we kick out page 5 with page 4, and we end up with this in memory. Now we access page 5, and we have to do the same thing. We have to kick out 1 of them. So again, we'd go backwards. We're not kicking out 4. We're not kicking out 3. We're not kicking out 2. So we're kicking out 1. So we would replace 1 with 5, and this would be our final answer. So if we count the number of page faults here, well, 1, 2, 3, 4, 5, 6, 7, 8. So now we have 8 page faults. So it was better than FIFO. Wasn't as good as optimal, but it was clearly an improvement over FIFO. So any questions about that? Yep.
If it's done like sequentially, when would we have a tie?
Oh, yeah. So the question is, if it's done sequentially, when would we have a tie? So you would have a tie only in the case of like multiple cores or multiple processors that might actually try and access the same thing at the same time. So for these questions, they're all sequential if we assume 1 core, so there won't be a tie. But that's mostly there for practical matters. If it looks like a tie, you just use FIFO to break it. Okay, so this least recently used kind of sucks practically, so it actually works fairly well. It's just whenever you go to implement it, it is a pain. So if you want to implement this in hardware, well, you have to search all the pages. So you have to search all the pages in memory and actually do the traversal, which is like order n, which really, really sucks. So you could implement it, and you'd keep a counter for each page that essentially says, oh, when was I last accessed? And then if you have to replace a page, well, you could save that clock. You save the time on each page, and then you search them all to find whatever the oldest one is, and then you kick out the oldest one. But that involves saving a clock for every page, which is going to take some space, and scanning through every page, which is going to be really, 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 really slow. So you could do it in software. We could be like, oh yeah, well, linked lists are 1, they're constant time. That's great. So let's just create a doubly linked list of pages. And then for each page reference, well, I would just move it to the front of the list. And that way I maintain that the order of my linked list is the order of accesses. So if you just have an access to it, then it goes to the front of the list. So if you do that, well, then your linked list is actually ordered by access time without having to store it explicitly because you're just moving it up. Now for replacement, that's really, really simple. You could just look at the back of the list and say, I'm removing that page. But the problem with this is that the constant really, 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 really matters, because that constant of adding that page to the front of the list happens for every single memory access on your machine. So every single byte, you would have to do essentially 6 pointer updates for every memory operation you use on your machine. So it would slow down your computer by like a factor of a lot, by like several hundred probably on each reference. So it's not going to be practical whatsoever. And there's also, it's even worse if you assume multiple processors, because you would have one queue and then say 8 processors trying to all manage that queue at one time. And as we know from lab 4, that's a data race. So all the processors would have to contend with updating that list, so it'd even be worse than that constant time thing. So this would just be absolutely abysmal, and you just couldn't do it. So what we settle for is an approximate least recently used. And we think that is okay because least recently used is kind of an approximation of the optimal algorithm. If you think about it, it's just using the past to predict the future instead of actually knowing the future. So there's a lot of different tweaks you can do to implement more efficiently. So next lecture, we will look at the clock algorithm, but there's also a bunch of different ones. There's least frequently used, which is a little bit different, where it counts the number of usages. There's like using 2 hardware queues. There's adaptive cache. There's all types of different algorithms with different trade-offs, and we will just see one particular one that's a bit more easy to understand in the next lecture. All right, so any questions? Next lecture will be a fun one because I animated a little clock. It's lots of fun. So, goal of today, we use page replacement algorithms to reduce the number of page faults because we're now taking advantage of disk being bigger and trying to fool our operating system into using more memory than it physically has. So we saw 4 algorithms. We saw optimal, which is good for comparison, but not realistic. Random, we didn't do an example of it because, as the name implies, it's random. But if you actually analyze how well random works, well, it actually works surprisingly well. It beats FIFO quite handedly because in practicality, it avoids the worst case. If you just randomly make a decision, you can't really make a bad one, or you're least likely to make the worst decision possible, which FIFO tends to do. So it actually kind of works in practice. FIFO, we saw, kind of easy to implement, but has that anomaly where we give it more RAM and we have more page faults, which kind of sucks. And then lastly, we saw least recently used, which gets close to optimal, but it's expensive to implement, but it's the first one we saw that's actually practical. So with that, just remember, pulling for you, we're all in this